In this lesson, we shall focus on applied mathematics APM 3711, numerical methods 2. We shall look at Adam's multi-method and many other methods that will pertain or include, amongst others, our famous Paddy approximation being applied to different questions relative to what you looked at previously. Right, there's a method we made mention of. We computed errors in our previous exam that pertained what we call the Euler method, but now what we call the simple Euler method. But today we'll have a perfect opportunity to apply these methods to pass examination questions and see how not just computing errors, but applying the method actually works. Right, so use the simple Euler method for the differential equation with h equals 0.2. But the differential equation given is dy dx equals x over y at 0 is 1, to get y at 1. So we're given a step, right? We mentioned a step, length of 0.2. Compare your numerical solution with the analytical solution of the actual differential equation. If you solve this differential equation, the solution we get is y squared equals 1 plus x squared. Now the question is, how do we solve this simple Euler method? Right, so we did not solve it last time because it was not part of the exam paper we looked at. But here in this exam paper, the students were asked to solve this particular problem. Let us start by discussing this step by step. So to discuss this, we take note of the following, that for the simple, Euler method, the algorithm is yn plus 1, which is yn plus h, fxn yn. Sometimes you write it as y sub n h y primed subscript n, where x0 is 0, y0 is y sub 0 is y at 0, which equals 1, because that's what is given. And there's something we call the multivariable function f of x and y, which becomes our differential equation always. And the differential equation is x over y. Always in this module, we normally use the notations. The notation, the differential equation is f of x and y. We call it that way. And to continue now with our notion of the simple Euler, we will arrange the calculations. Right, so I'll arrange the calculations in the form of a table. In the form of a table with columns. With columns for, okay, we shall construct a table now for the simple Euler, and you can see that using a table, it makes it much easier. But for the x sub n, y sub n, for instance, we shall use the table x sub n, then we shall also have y sub n. Obviously, we shall also have y primed, yn primed, y primed subscript n, h, y primed subscript n, and we make the following sentence. We construct the following sentence and the following note, that the table will be filled. Right, the table will be filled one row at a time. One row at a time. We use X subscript n and Y subscript n to find Y prime subscript n, which is this. So the table will be filled one row at a time, as you'd expect. We use xn and yn to find. We use xn and yn to find Y primed subscript n. Okay. And to describe this is we then multiply. We then multiply by h to get hy prime subscript n and add these two Y subscript n to get yn plus 1 for the next row. Now let us look at this, but reason very, very carefully. We've just described what we're going to do, but obviously we shall do it, and that will make it much clearer when we actually put the method into practice and construct the table that we're talking about. For this step length h, which is 0.2. If we start with xn, for the step length 0.2, for the method of the simple Euler method, Y subscript n, we're going to have Yn primed. Okay, let us move this a little bit to the further right, because we shall have some numbers with several decimal digits until in our approximation attempt and technique. So we shall have also this. Okay, if our h is 0.2, yet we start with x0 and y0. What is x0 and what is y0? Okay, those ones, obviously the x0 and y0 we're going to put in the table, but are actually part of the what? Of the initial condition. So x0 is this one, 0, and then y0 becomes 1. So those are sort of the initial values, yeah? So now we then say our x0 becomes 0, but yeah, right? 0.0. Add 0.2. 0.4. 0.6. 0.8. 1.0. So yeah, we're just starting with 0, and then we're adding the 0.2. And so if we start with 0 and we add 0.2, we get 0.2. Another 0.2 is 0.4. Another 0.2 is 0.6. Another 0.2 is 0.8. Another 0.2 is 1.0. And then we'd have the yn. So this is the table. What is then the first one? 1.0. Now, we would remember something, that this is our y primed, but the y primed subscript n, we've already mentioned that it is fxan yn, which is this one, but it is exactly according to this. The derivative y prime is it's xn divided by y subscript n. Right, so that is what we're going to plug into this one and then get what we want. So if you have the first one, the y0, it's 1. We write it as 1.0, just to one decimal place. And now we look at the next one, when our 0.2, 0.4, we add 0.2 and we get to 1.0. Next, let's look at the y values. So to actually be able to obtain these y values, we obtain these y values most essentially as follows. Right, would remember that we have our Euler, as we stated it, but we're going to have to give a statement of the method again. Right, because now given a y value, the subsequent y value in what we call, so this is what we call the simple Euler. It is the same as the Taylor method, but it is Taylor of order 1. Taylor of order 1 has the name Euler. And now we're going to take a look at how we do this. So we have, this is the formula for what you call Euler, simple Euler. And it is actually what we use. Okay. Now, we have, for example, so I'll put everything in the table, but yeah, the table makes it easier. But we can also do without the table, but it's just that everything is going to be mixed up. We might even get confused. So, then we have this. Then we have this. Okay, yeah, just the table. Right, that's our table. That's our table. Now, so now we have this one. Okay, let's start filling this table up. So what is y primed? Y primed we can do first for this one. Y primed, like, this is y0, x0. So y0 primed is going to be x0 divided by y0. x0 divided by y0. So x0 divided by y0 is like 0.0 divided by 1.0. 0 divided by 1 is a 0. So let us call this one 0.0, but just 0. You just want decimal place for consistency. Next. Now we're going to take h and multiply by h by y primed subscript n. What is h? It's 0.2. H is 0.2, and then multiply by the primed. Okay, so that is 0.0. Okay, so let's continue. Next, if you look at the 0.2, now we want to get the subsequent y value. If this one is y0, y0 is 1.0. What is y1? Let's just come here. Y1, according to these, it's going to be, according to these, it's going to be Y1. It's going to be Y0 plus H, Y0 primed, according to this. Okay? So, just the formula for the Y, for the Y1. Okay. Yeah, pay particular attention to that one. Okay, let's continue. What is 0.2? 0.2. Okay, let us look at this here. Let us look at this here. Yeah, at 0.2, let's look at the y, because this is actually our y0 and this is our y1. Our y1 is this. So y1 is going to be y0. You add y0. Y0 is 1 plus 0.2 for h plus y0 primed, which is this one. Okay. So, but you can say the y0 prime is already 0. So 0 by h is going to be 0. So this one is going to be the same as the y0. The y1 is going to be the same as y0, which is 1.0. Next. Now let us look at, so you're allowed to write like this in the exam. I mean, that is the point we're making. But also the questions we normally face is, can this be done? I mean, are you supposed to know any software programs for the exam? Are you supposed to know any Python programs or any other programming numerical computer programs? You don't need to know any computer programs for exam purposes. Your calculator is enough. Okay. Now, if you look at that, now let us get the next thing here. So here, this is y1 prime. What is y1 primed? Y1 primed, according to this, is going to be x1 over y1. What is x1? X1 is 0.2. Divided by y1 is 1, which is 0.2. Now, at this point, you need to multiply h by the y primed, by the preceding y primed. H is 0.2, and you multiply by 0.2, and you get a 0.04. Okay, you can just verify that one, just to make sure that we understand exactly what is happening. We are effectively saying you multiply, at this point you multiply h by y primed. So we know that h is 0.2, and the y primed is 0.2 again. The answer, 0.04. 0.04. Right, 0.04. Next. Next. You'd have the next one. xn, which is 0.4. Okay. Now, when you need to get the y, so this is, so that you remember, okay, this is like n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, or you can write like in the same way like the table is constructed. So you can put n and then put 1, 2, 3, 4, so that you remember the positions of these things, because sometimes you can get mixed up. So if this is n, for example, this is 1, 2, is 0. You can start from 1, of course, but normally we start from x0, y0. So it's going to be 1, 2, 3, 4, 5, like that. So you have this. Okay, now let us finish this up. Okay, let us finish the table up. So now for the simple Euler, when the step is 0.2, right? So now we're putting the ones to make sure that we understand this one is y2 according to n equals 2. So if it is y2, then we come here. What is y2? Right, so we can write these things because now we're getting lots of these. So y2 would be, according to this formula, 1 plus 1, 2, is y1 plus h. y1 primed. So what is y2? Is y1 plus h side. So let us finish it in the table here. So what is y1? y1 is the one before, which is only 1, plus h is 0.2 always, plus y1 primed. And y1 primed is this. So you can see that these things are using this row here. So it's y1 plus h, y1 primed. Right, so we're going to use a calculator. So we're going to do like this. And then say it is exactly the following. Okay, so according to this, it said it is y1 plus h, y1 primed. Just one sec. So you're going to have, for example, y1. What is y1? Is this one 1.0? You can just put a 1 plus h 0.2 plus y1 primed 0.2 again. Okay, we already know that. 1.04. Know that you can always find a way. So, which is actually exactly 1.04. .04. Okay. So now let's do the next one. To do the next one, you're gonna get y1 primed. Okay, good. Okay, now we have some decimals that are coming up. So let's just use our calculator. So set ready your calculator. It's enough. In the exam. So we know that y primed, which is the derivative, is x over y of the preceding one, which is x over y. So we practice with this and then say x is 0.4 over the y, which is 1.04. And then we get this one. We get exactly that one. They are 0.384615. Good. Recurring. So this, after this, then it's going to be 384 again. Okay, because of the line on top. So now we're going to put that one here. 0.384. 0.384. 61. 53. 84. Okay, so we just divided, for the y prime, we divided x by y, according to the differential equation. Obviously, y n primed is x n divided by y n. Okay, now we just do the, we just multiply h with the y primed. So now if you multiply h with the y primed, we are able to get the following. So in other words, we're going to take our calculator again. Okay, just practicing the simple Euler. Okay, we've already got this one, and then just need to multiply it by h, and h is actually 0.2, so we have the 0.2, and then we get the answer. So the answer we're getting is 0.076923 recurring, and then there's going to be a 0.76 again, if we write a bit more decimals, because, yeah, this is repeating. So now it means we have 0.0769. And then 23. 0.76. Like this. So now, what is the next thing? We continue. Let us complete this table. It's not going to take us very long. Now we're doing like n equals 3 and we have 0.6. N equals 3 equals, and then we have 0.6. What is our y3? What is our y3? So at this point, our y3 can just get from the Euler, simple Euler formula. So our y3, according to this, when y3 is when n is 2. When n is 2, because it's 2 plus 1, then this one is going to be y2 plus hyn, and the n becomes 2 for y3. So it's 2, 2, then it is 2 plus 1, which is y3. Okay, let's get y3 now. So to get y3, which is hy2, y2 primed, yeah? y2 primed. Okay, let's come here. What would y2 be? So there is y2, which is this one. y2 primed is this one. And then you just put the h, You multiply by h by the y2 prime, and then you're able to get the result y3, and then you put it here. Okay, let us do that one. Okay, I know that this is pretty clear now so far, because we're just repeating, just growing this table. But we shall, get into 1.1, into y at 1. That is the final to say where are we going with this table. We are going to 1. Once we get to y at 1, then that's what we want, because we want to find the approximate value of y at 1. Okay, but now I know that we can go on without the table. We can do the calculations, etc. But the table makes it a little bit easier. Perhaps it provides us with another way of reasoning. Okay, but as we said already, we're going to start with the yn plus 1 is yn. So in this case, it's going to be y 1.404. Okay. Not 0.38. 46153. 84. Okay. 1.116923077. That's what you're getting. So that's what you're going to put here. So it is 1 point, excuse. Right, is 1.11. We saw in this calculator. 69. 1.11. 69. 23. 077. And then you would have y primed, yn primed, which is x over y, the preceding one. So this is, for instance, y3 primed, and it's going to be like x3, y3. So let us do x3, y3. We divide them. x3 divided by y3. Okay, so x3 is 0.6. Can do 0.6, and then we divide by this one, 1.11. 1.11, then it is 69, and it is 23, and it is 077. Okay, and then this one is the answer we're getting for that one. So it is exactly what? 0.53719. Yeah, 0082. Yeah, that's what you're getting, and it's the correct answer. So 0.5371 90082. So now let us continue with okay, want to get the answer. The answer is the estimate, the approximation of 1.0 according to the simple Euler, but we can use other methods. Simple Euler is one of them, but we can also use the Adams-Moulton, which we've seen, and it's going to feature in the next couple of minutes. But yeah, a different problem to that, and we shall also look at the finite difference technique, finite difference method. Okay, let us look at this one. Now it's easy. We just find the h times y primed. But as said already, where are we going with this table? We are trying to find one y at 1. Y at 1. So, okay, we have this one here, which is up to this is 082. Let's see, 719, 082. And obviously 01982, then it is 82, then with a 6. But we want to multiply these by 0.2. So now, if you multiply it by 0.2, you get 1.10743.80165. So it is 0 point. You're going to the calculator. 107 438016. 1074 38016. Okay. Let us continue right now and get the answer. Now let us move on to the next step. The next step is n equals 4, and that gives us like what we call x4. And let us get the following x4. So now, in our x4 analysis, okay, we're getting x4. Right, so x4 is 0.8. But what is y4? We come to this. Y4, we use the formula for Euler, simple Euler, is this one. So you can say y4 becomes y3 plus h, y3 primed. Okay, good. We plug in everything. So now this is going to be like y3 plus h, y3 prime. y3 plus h, y3 prime is going to give us y4. Okay, that's what we do. So let's just complete the table. Okay, I'm practicing a simple Euler because it comes, this is a past exam question, and we're tackling exam papers, by the way, in this discussion. So y3 is 1.11 69. We're taking this one as it is. 1.1 is like y3, and then h y3 primed. So it's 1.11, then 69, 23, 077. Okay, then you have h 0.2, 0.53, 71. Okay, then A2. So now let us get this one. What is the answer? It's 1.224361093. But now this actually is written like 1.224361 Okay, this one gives us what? It gives us the y4. Let's separate by convention. In this module, we begin from x0, y0. So we begin from n equals 0. Let's separate. I mean, these are just positions, and you can begin from 1. But now, normally the initial value is the 0th value. Okay, let's start now. This y primed, yn primed. Okay, yn primed is xn over yn according to the differential equation. Is xn over yn. So y4 primed is going to be like x4 divided by y4. Okay, what is x4 divided by y4? So what is x4 divided by y4? Okay, so what is x4? Right, x4 is 0.8. 0.8, and once again, you can write like this, and you have 0.8, and you divide by, right, that is x4 divided by y4, which is 1.2243. 1.224361094. Okay, so I know the 094 is 093 difference, but now this is rounded off to 094 because this calculator gives fewer digits than a computer program is able to give. But obviously, I mean, there are always errors in the rounding off, so I'm sure that it's always taken into account. So now here we then have 0.65340201. You put it here. 0.65340201. Okay, one of the things that is very important here is time in the assessment of these, because you can see that you're just busy with the calculator and time flies so fast, so fast. So you need those strategies. Okay, now you got this y prime, which is this one. And then now you must take this one and then multiply h by y prime. So h is 0.2, which is the step length, so, or the step size. And if you do that, you're getting 0.130680402. It's often very tricky to finish this one. Numerical methods, because your calculator is working and you need to make sure you write, and now you just writing so many digits here. And the time before you check, it's just way gone. So 130, then 68, then 0402. Okay. Next, we have finally, we are at 1. Finally, we are at 1. Right. So if finally we are at 1, we're able to get the following. Let us check this one. At 1, we are able to then say, what is Y5? We come to Euler, because that is what we use to get the subsequent. So Y5, the formula for it is when n is 4, so it's going to be like Y4 plus H Y4 prime. So that you have Y5 is Y4 plus H Y4 prime, which is this. So we're going to take this one plus H times this. Then she'll get that. And that becomes our Y value, Y at 1, which is actually what we worked so hard to achieve. Right, so, and then this becomes the following. Y 1.22 for 3. 61, 1.22 for 3, 61094 plus 0.2 times 0.6534 0201. Okay, let us check what we're getting here. Right, we're getting 1.355041,496. That's what we put in here. So it is 1.355041,496. And therefore, this is the answer we want. So we don't have to continue with the rest, because now we can then say, hence, y at 1.0, which is just 1, is approximately 1 point. This is at the step number 5, which is 1.355041,496. That is the simple Euler method. Simple Euler method. Okay, let us continue and determine the next one. Determine the next one. What is the next one? The next one is another question on this. Okay. So let us look at this one. Okay, that was still the simple, it seems still a simple Euler. Okay, there's part B where you need to continue with this method, but also now have more steps to practice. You have more steps to practice. So with the more steps to practice, we'll just be making sure that if H is 0.2, then it's 0.1. 0.1 is more steps. How is it more steps? How? Because we start from n, then we have xn, then we have yn. Then you have what we have actually been able to see before that. Right. So you'd have exactly that one there. Let us see. You'd have 0, 1, 2, 3, 4, 5, 6, 7. Okay, so we're gonna need more. We're gonna need more than this. Now, if you come here, then you're gonna have x, n, y, n. Okay. Okay, now, what then are you able to achieve here? So like we've seen before, you have the yn. That's fine. Okay, so like we've seen before in the previous table, we got x, n, y, n, and then now we also need to get the y primed, yn primed, and then you're going to get h, yn primed. Okay, let us do the things here that need to be done. Okay, now this is going to be a bit more work. What we're going to do, we're going to do it twice. But we have to try to be faster. So you have this one just to make it more visible. N0, then N1, 2. Then you have 3 with a simple Euler. Then you have 4. Then you have 5. Then you have 5. Okay, let us do the following. Let us do it together. Okay, we're already familiar with the method, but now we're just using a different step size in this exam. And now we actually need to practice and make sure that we are just aware of what needs to be done. We're using a table to make sure that we organize our information and don't get confused by too many equations. Let's start with the first x0. Okay, x0 is still the same and y0 is still the same. So x0 is 0.0, y0 is 1.0. And then now with the x0 is 0.0, y0 is 1.0. Then now we move in steps of 0.1. So it's going to be 0.1, then it's going to be 0.2, then it's going to be 0.3, then it's going to be 0.4, then it's going to be 0.5. But still you're not done because you must get to 1. So let us continue this side. So we shall have n, and then xn, and then yn, and then you're going to have ny primed, and then you're going to have hy prime, yn primed. Okay, good. Now we have 6. Okay, let's see. Now you have 6, 7, 8, 9, 10. Okay, because here we stopped at like 0.5 and then we're going to do 0.6, 0.7, 0.8, 0.9, and then 1.0. Okay, then we're going to be at 1, at y at 1. Okay, so let us do this. Now we're just practicing with this, but I know very well that we're very familiar with the method already. Now to practice this very well, let's start for this particular problem, and then we move to other techniques of that you need to learn. Now, to start with here, we're gonna have, for example, this one, and then what is y primed? So it's gonna be y0 primed. Okay, but as we said, Our usual Euler formula I need to write down. If they say simple Euler, normally they don't give this one, but you write yn h yn primed. So, all right. So now, all right. So now, in the end, let's check. Okay. Now we're gonna divide. So y primed, like y0 primed, is gonna be x0 divided by y0. X0 divided by y0. 0 divided by 1 is 0. And then now we're gonna continue, and then this one, h times y primed. H times y primed. So if you're gonna say h, which is 0.1 times y primed is 0.0. Let us do this one. Okay, let us do this one. What is this one here? This one is going to be 0.1 for which is x1. Then you're going to get the y1 need to get. So y1 according to this, when n is 0, is y0 h y0 primed. So what is y0? Okay, so now already we know that y0 is this one and y0 prime is this one, and then multiply by h. But we know h is 0.1 by y0. It's going to be 0.1 by 0. It's going to be 0, and therefore it's going to leave us with y0 for this one. And now we're going to get to this. I said we're going to be a little bit faster because we just are trying to highlight the method. Then let us look at the yn primed. So yn primed is going to be this one. It's going to be y1 primed. According to this, it's said already, the yn primed is xn divided by yn. How do we know? Because of the differential equation. So it's going to be xn divided by this, which is 0.1. Okay, because it's like 0.1 divided by 1. 0.1 divided by 1.0. 1.0 is like 1. So this is actually exactly 0.1. But now if you then say 0.1 times 0.1, okay. So yeah, we're moving. So if you have 0.1 by 0.1, because it's 0.1 is h, by y primed is 0.1. So you're doing another 0.1, which is 0.01, which is 0.01, 0.01. 0.01. Okay, good. 0.01. 0.01. Okay, let's continue, please. Then when you have 0.2, right, so we need to get the next y, because this is like already x2. For n equals 2 is x2. Then it's going to correspond with y2. What is y2 according to the Euler? Simple Euler. Y2 is y1 h y1 prime. So let's just do this. y1 primed with the h. Right. So which means that we can have y1, which is this one, and then we're going to add the h y1 primed, which is this one. So it's going to be 1.0 plus 0.01, which is 1.01. Okay. Then now we're going to have another y primed. In this case, it's going to be y2 primed. Y2 primed is x2 divided by y2. X2 divided by y2. So x2 divided by y2, 1 point that, which is 0.1980, 0.1980 recurring, 0.1980. And then you see the 1980 is going to be like 1980, 1980, 1980. So which means that here we're going to have 0.1980, another 1980, 2. Okay. Multiply by h. So which is times 0.1, which is 0.198. Let's check this one. 0.0198 recurring. So it is this one. It is 0.0198, not 1, 98, not 2. That kind of thing. So that's what you're going to have here. Let's look at the n equals 3. Then we have x3, then y3. Y3 is going to be y2 plus h, y2 primed. So we have y3, which is y2 plus h, y2. So y2 plus h, y2. Yeah. Y2 is this one plus h, y2 is this one. So you add them up. What do these things give us? So if you add this one and this one, you'd get 1 plus 1, 1 plus 0, giving us a 1. Then this is 0, 1. But 0, 1 with a 0, 1 is going to give us 0, 2, 9, 8. And the rest of the digits repeat. 0, 2, 9, 8, and the rest of those digits repeat at position 3. Yeah. So it's going to be 1 point, excuse. 1 point. Okay, let's do this. 1 point. Okay, now at 3, it's going to be 1.0298. 0198. Okay, so okay, now you divide the two. Yeah, divide the x and the y. Okay, so which means you're going to divide the x and the y. Okay, yeah, you can do like this. 1.02980. 198. 0.291. Okay, let's check. 0.291318142.5. Okay. Right, so to check this one out. So you can write, doesn't matter. At position 3, 0.291318142.5. 0.942. Multiply by, okay, it's approximate. You can write this as much as 4.3 because there was potentially 5 there. But I'm being consistent. So now you have the next one, which is, I said right there, just these discrepancies. You can see the 2.5 multiplied by 0.1 h, because it's h times that. Let's see what you're getting. 0.2913184. Okay, just that the decimal place is going to shift once. So it's going to be 0.291318142. Okay. Let us look at the next thing. At 4. Okay, now at 4, it's going to be y4. Y4, we must use Euler. Okay, y4, according to this, n plus 1, yn, h, that. So y4 is y3, h, y3 primed. Okay, good. What is y4? You can take y3 and then take h. So you add this with that. Okay, so you add the first y and the last h that. So adding them up, it's going to give us, let's use the calculator for this one. Okay, maybe you should have not. Okay, so we're going to take this y3, 1.02980,198 plus 0.0291318142. So now, okay, what is this? 589,33794, which is not 5, 8. 8, then what? 933,794. Then you have the y primed, yn primed, you divide the xn and the yn. So, okay, obviously I know that you get the drift now. Okay, you actually surely are getting the drift here, but we're practicing with these methods. So now we're gonna you divide the x by the y. Let us do division. So the x is 0.4. You divide the 0.4 by what? By 1.0, 5. 8, 9, 3, and then what? 3 again, dividing by this one, dividing this one by that. So you have 794. Okay, then what is the answer to this? This is a simple Euler, and it gives us y4 prime. Right, so y4 primed is 0.3777. And then we have 3844. Yeah, let's write it here. Okay, and this one, it's 0.3123 of the sevens. Then there is 3844. Okay, then you're going to just multiply this one by h, and h is 0.1. So you multiply it by 0.1. So which is times 0.1. which is a 0. What? Not 377, then 3844. Not 3 1 2 3 3844. Okay. So we continue with the Y5 now. And to get the Y5, we use again our simple Euler equation. Once again, this is the same as Taylor, but Taylor of order 1. So now it's going to be Y5. And Y5, according to this, it's going to be Y what? It's going to be Y4 plus H Y4 prime. What is this? Okay, what is Y4? Okay, let's continue. Right, so Y4 is this Y5, excuse, yeah? When n is 5, then it's a Y5, then we have Y4 plus H Y4 prime. So Y4 plus H Y4 prime is like this one together with this one, we're adding them up. So let us do, which is Y4, which is this one, 1.058933.794 plus this one, 0.03 777 3844, which is 1.096. 1.096. Okay, let's check. Yeah, that's what we're going to put. 1.096, then 707, then 638. Yeah. Okay, good. That's what we're going to put here. 1.096, 707, and then what? 638. Okay, then you're going to divide them. So the yn prime is x, it's x5 divided by y5. Okay, so let us divide x5 by y5 using a calculator. Right, so we're putting everything in the table, and once again, the table makes life easy, we believe. Okay, we believe. So, yeah, let us do it. We divide x5 by y5 according to the y primed, yn primed formula. So we're going to do 0.5, we divide by 1.096 707,638. Then we get the answer, which is 0.455. 0.455 at y at this one, yeah? 0.4559100 that. So, yeah, 189. So now we put that one there at step number 5, 0.455, right? 910018. So now, if then, okay, we have this one. And then just multiply this one by what? By h, which is 0.1. Okay. Right. So now we're going to do the multiplication. Okay, so multiply by 0.1 by h, which is 0.1, which is just, it shifts one decimal place like that. So giving us 0.04, 0.04, 0.04 5591 0018. Okay, let us continue. Okay, yeah, and then now we get this one, then we go on, and we're going to do the sixth one. Okay, we are finishing, please, this table, and then we're going to move on to the next concept. This one is going to be essay to assist a different step size. So if it is now we want to get it n at 6, then this is x6, then this is y6. But if we know that the yn plus 1 is yn, h, yn prime is a simple Euler, then we can be able to get our y6, which is when n is 5, and h, y primed 5. Okay, y primed subscript 5. Okay, let us get this answer now. Now to obtain the answer, you need to obtain the y6. What is y6? So to actually obtain your y6, you'll have to take y5 and then add with the other y5 primed. So if you have y5, which is exactly what? Which is exactly this one, and then you add the h, y5 primed, and then we shall get the answer. So let us do that one. So to get this, we're gonna do it like this, and yeah, I'm sure that you already get the drift, but the aim is just getting the answer. So y5 is gonna be this one, which is 1.096707638. Okay, then you add with the other one. Okay, you add with this one, 0.04 55 910018. Okay, you get this one, which is 1.142298. That is going to give us our y6. Awesome. So let us get our y6. We have already seen that our y6, it's going to become what? It's going to become 1.14229864. Okay. So we continue. Okay, now let's do this one. The prime. To get y6 primed, we know that yn primed is xn divided by yn. So we divide this one. We divide x6 by y6. So we get the prime. Okay, we're almost done with this table. Okay, just use the table here because maybe it's the same thing we can use, but too many equations get mixed up, and if the sequence is too long, too many iterations, then you get confused. You get everything mixed up. So that's not 0.6. You get this one, and then you divide by 1.14229864. And then let's get the answer. So yn prime, which is 0.52, then another 52, and then a 66, and then 877, right? So we're gonna get this one corresponding to the 6. So is not 0.52, and then another 52, and then 56, and then 87. Okay. Yeah, there can be discrepancies in the rounding, but in the rounding off, yeah, I know very well. So, but now we multiply these by the h till, okay, repeat it so that you understand better, because sometimes if you just repeat the steps. So it's 0.1 and then you get the answer. So now this one is 0.052, 0.052, 52, 0.052, 56687. So now, okay. Okay, now let's continue, please, and get the answer. And get this Y7. We know that Y7 here is going to be Y6 plus H, Y6 according to simple Euler, the prime here. So in other words, we are saying Y7 is Y6, H, Y6 prime. So now this is Y6 and then H, Y6 prime, and then we add them up and it's going to give us Y7 and then we're done. Just almost done with this table. My goodness, I know it's dragging, but I'm gonna have much faster next subsequent things. So it's 1.1422 9864, which is 0.052525667. So now, which is at 7, 1.1948224,309. So 1.194 824, 1.194 yeah, 194,824, then 309. Okay. Now let's move on to the next one. Then we're going to divide to get to, for instance, Y7 prime. That's going to be X7 divided by Y7. Dividing. Okay, we're finishing this simple Euler, please. But now I'm sure that after this, then you'll never forget the simple Euler because we've done like 2 examples in this exam paper. So I'm sure that you'll be like, okay, you can remember it always. So it's 0.7 for the X7. You divide by the Y7, which is 1.194, and then 824, and then 309. Okay, so what is this? 0.585. All right, so we're getting 0.585 in the case of that one. 0.58. Yeah, okay, that's fine. So it is 0.5858. 0.5858 60192 multiplied by 0.1, which is 0.1. So now, not point that one. So not point, we've seen. Let me see that everything is above board on Y7, 192, yeah? And then it's 0.058 you saw, and then 58, and then 60, and then 192. But pay attention to the fact that this one just shifts the decimal point. Yeah, because you like multiply by 0.1, so you divide by 10, so it's 0.0, and the rest of the digits are the same. Okay, now we're getting Y8, getting closer to what we want. Right, so getting Y8 is, according to this, Y8 is actually exactly Y7 plus HY7. Y7 is this, and HY primed, Y7 primed. So we have the following. All right, so let's get Y7. 1.194 and then 824, just practicing, and then 309, using this exam paper to practice because this question just repeats. And then plus now you have this one, which is 0.585860,192. You add up, and then you get the 1.253410328. Check that out, and that is corresponding to that one, right? So yeah, that's fine. So it is 1.25 341 0328. So now, okay, now you multiply by you divide the things. So you divide x8 by y8, and then you get the answer. What is x8? 0.8 divided by y8, 1.25341, and then 0328. 0.8 and then 1.25341 028. Okay, so 0.638. Okay, this one is going to be exactly 0.63, yeah, 82, 58, 66, see, 29. Okay, yeah, on average, you can write it like this. You're going to write it like this. So, okay, let's write this one. For 0.8 next to it, so after the division of the primes, the right, so let us see what you're getting. It's 0.63, 0.63, 82, 58, 0.63, 82, 58, 662. Okay, now multiply everything by, multiply this prime, yn prime by 0.1. So we'll never forget this one, and then multiply by 0.1, which is the step size h, or the step length, called it last time. So that's going to be the 0.06. Right, so it's going to be exactly the 0.06. Let's check this one for the corresponds to the 8. So is 0.0638 with the 662. Okay, good. So it is 0. You've seen that already. 0.068 or 63. Okay, 0.06382. 58. And then okay, 0.063 82, 58, 662. Okay, something like that. But I mean, I know very well that they are just rounding off errors here, and these might get to like 63 depending on the digit you find after the two. Okay, now there is this one. We're finishing really quickly this question, and then now we're going to move to the formula we have. So obviously the formula is clear now. We need to get our y9, but the formula for y9 is going to be y8 plus h y primed 8. So now, okay, so it's right. So now you have the following. Okay, so you're going to have y8 1.25 341 1.253410328 plus 1.253410328, and then you add this one, not 6 382 0.06 382 58 662. Okay, so we're getting 1.317 and then 236194. So I'm going to write here 1.3172 and then 36194. 1.3172 36194. Then you're going to divide them. Divide the y9 primed is x9 divided by y9 according to the differential equation. So yeah, we're finishing, please, and then moving to the next question. So that's going to be the x, which is 0.9. You divide by, that's x9 divided by y9, which is 1.31. I said right, the rounding off errors, we expect them. So the penalty, I'm sure, is minimal. 361. And then 94. 3172 36194. So now, okay, so you have this one, 0.6832487762. 6832487762. Okay, so that's what you're getting. And then now you want to multiply by 0.1. By 0.1. 0.06. We're getting 0.06. So it's going to be a 0.06 for the y9. 0.06 what? 83248769. Okay, I'm going to write it. So it is, write it like so. 0.068. Okay, and then what? And then 32, and then what is it? 32, then 48. 48, and then from the calculator screen, 762. Okay, now we say Eureka. We've got it because we have the answer. What is the answer? Okay, this becomes our answer. What is our answer? Our answer is Y10. Y10. What is Y10? Is 1 Y9 H Y primed 9. Okay, good. So now let us get the answer. So we're going to take Y9 is this one plus HY prime 9. You add them up. Okay. 1.31. 72. 36. 1.31. 72. 36. 194 plus. Okay, that is that. And then we have the 0.68. And then you have 32. And then there's 48. And then 762. 1.38. 1.38556107. 1.38556107. Okay, and that is the answer. We're done with this simple Euler. And then now we're going to look at other sections. In other words, y at 1 is approximately 1.38556107. We've gone through some exercise. It was really a good exercise. Then we stop there. Then we don't continue to the rest, because if we continue the rest, then we want to get the next step, like y11, and we don't need to get y at 1.1. So we are stopping here, okay, for this particular problem. Now, then the next subsequent question is we need to compare your numerical solution with the analytical solution, this one here. So now the couple of things that we need to take into account as we analyze this next problem. So in other words, we note that the analytical, right, so the analytical solution is y squared, 1 plus x squared. What is this? Solve for y and check the square root on the left, the square root on the right. Plus or minus the square root of 1 plus x squared. So that is sort of the analytical solution that we're going to have. But obviously, because our y is positive, so which means that we can have a y equal positive square root. And this is the answer we're getting, because now the y is a positive. Y0 is positive. So if you do use this one, y0, you get a 1. But if you use this negative, then y0 of the plus or minus is not plus or minus, because of that. So obviously, we know from y squared we get plus or minus there. Okay, so this is what we're actually able to achieve. But now we want to talk briefly before we move forward in terms of the analytical solution and its significance. The analytical solution is justified by the fact that this is separable. Right, this differential equation is said to be separable. Right, it is separable because you have dy dx equals x over y. And this means that you have dy, you cross multiply. So it's going to be y dy is x dx. And then you take the integral both sides, meaning that you have the half y squared is half x squared plus the arbitrary constant c of integration. If this is the case for the separable differential equation, we can solve. Obviously, you can solve this using separability. And then we have y at 0 is 1. Okay, now, if we agree that y at 0 is 1 together with half y squared equals the following, equals exactly half x squared plus c, which means that y is 1, which means half of 1 squared, half of 0 squared plus c, and therefore c is 1/2, which means that you have this one, which is half x squared plus we're getting c equals 1/2. If you divide through by half, 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 we're getting y squared equals x squared plus y squared. This becomes the actual analytical solution that we are able to get. But also now with this analytical solution, we take this analytical solution and we make y the subject, because we actually can be able to express y explicitly as a function of x. With this mentioned, we are able to move on to the next problem. Right. So if we then have these here, right. So if we then have these here, would have the following. Right. Right. Okay, we're going on. We're going on, please. I will just speak about the analytical solution here. Um, right. Okay, good. So now, then if we then saying here, this is the answer we're getting. Okay, but this is what, remember, we need to compare your numerical solution with the analytical solution. That we have got the analytical solution by using the method of the solving differential equations, and then we are done. So now let's move on to the next thing. Let's move on to the next thing. Okay, in view of the analytical solution we need to compare with, we note that, for example, at x equals to 1, this gives y 1. Y 1, which becomes what? We've seen, therefore, is 1 plus x squared, which is the square root of 2, which is 1.41. Use a calculator. The square root of 2 is 1.41. We know this one very well. For 2, and then you have the following 1.41 for 2. What are the next digits? 135. 135, then 62. 62. Okay, let's pay particular attention to this and see what this gives us. In the case of the simple Euler method, I want us to discuss this analytical solution comparison that they said in this exam must be one was compared with. But also we have here the use of our table, the exact solution. So you have the exact solution, which is then Euler. It is Euler with h equals 0.2. Euler with, okay. Let us look at the 1.41421356. Okay, when H equals 0.2, we have already got the answer. You remember we got the answer. At 0.2, we got the answer, and this was the answer, yeah? Right. At when we're using the 0.2, 0.4, 0.6, 0.8, we got the answer, which was 1.355, And then the other one that we got for the other one, whenever we are using the H equals 0.1 a step size, we got 1.38556107. So we put here. Right, so now we come here and then we then say it's 1.355 for the 0.2. That's what we got first. 1.355, then there's a 041. Then you have the right. So you have 355, then 041, and then you have 496. And then here you have 1.38, 1.3855. And then you have the 6107. Then you would have the error. You'd have the error. Okay. You would have the associated error that comes with the solution. Because we know that according to these, once again, we have used the calculator. We can launch the calculator again and find the approximate solution or approximate value of the square root of 2 as a decimal fraction. So it is 1.414213562. Okay, that's what we have written. Now, okay, what are we saying here? We are saying the actual analytical solution. The analytical solution. Right. So we are able to see that we have here what we call the analytical solution. Right. So if you have the analytical solution, then we're going to have that square root is the answer. Good. But what then becomes the meaning of all these things here? Okay, so we have seen that if y at 1, because we want to get y at 1. Y at 1 is the square root of 2, which is this. So these answers are approximate this. The exact solution is 1.411356. That is the exact one. But with 0.2, there is 1.355 we got. Then with 0.1, we got 1.38, blah, blah, blah. Okay, so we can see that the exact answer is 1.4142, but Euler did not give us the correct answer. But also, when we have 0.1, a small step size, you have 1.38. 1.38 is becoming more accurate. But if you have 0.2, then we have 1.355. 1.355 is less accurate. So if you choose a big step size because you want to get to the final answer quickly, because now this one of 0.1, it took us very long. We took 2 boards. We had from 0.1, then 0.5, and then we went on to do 0.6, then to the next one. So we did 5, like 10 steps. And so it was long, yet the answer, the 1.38 is more accurate. But the 1.35 is less accurate. Why is it less accurate? Well, how is it less accurate? Well, because the final answer is like 1.4. So the 1.38 is closer to 1.4 than 1.35. 1.35 is further away, meaning there is an error, a computational error in the approximation method. And now let us compute the error as the big O notation. So what then becomes of the error? And also, how do we compute the error? Let us calculate the associated error of these. Right. So now let's use a calculator. If you use a calculator, we launch our calculator and we compute the error. In case of the simple Euler, we have an experience of computing the error as in the previous paper. We looked at how to compute the error. But if the exact solution is the one we get from the analytical equation. So we have 1.41421356 1.41421356. We subtract. Let us first subtract this one. 1 point for the 0.2, 1.355, 1.355, then 041, then 496. 496, which is the 0.0591720066. That is the error. So the error 0.0591 and then 72 and then 066. So that would be the error there. And then now let's look at the error in the case of the second step size 0.1. Right, so we're going to take the accurate one. What is the exact solution? Is actually exactly the square root of 2, which is what we have. So it is what? It is this one. So we punch it in here, which is 1.422. Right. Okay. Okay, yeah, let's look at the accurate one. 1.4142135. 1.4142135. Then 62. You minus 1.38556107, which is this one here. Okay, so it's 0.028. We're learning how to compute the error in the case of these methods. 0.02865. Okay, yeah, not 28. Yeah, then 65. Then what? Okay, then 2492. All right. So this would be the thing. All right. So okay, this was set was made to just take more computational time. And so, but let us comment on the actual significance of this and the actual implication of the answer. We write a note that in general here, based on this question, however, and the way we approach the answer, the first two answers we've got, right, note that halving, right, halving the step size, from h equals halving the step size from h equals 0.2 to h equals 0.1 has halved the error. So we have that the error has been halved by halving the step size. Right, by halving the step size. So now we have the error. So if you halve the step size, you halve the error. This is as expected. So this is as expected. Right, this is as expected since the global error, in the Euler method, is the global error is big O of H. and big O of H as the global error, that is proportional to H. Proportional to H. Right now, this is awesome news. It is awesome news. All right, so now we have celebrated the simple Euler method, but now let us move on to practice even more problems, but also more types of numerical methods in this module. Let us look at the next problem. So looking at the next problem, we have the following. Simple Euler, we've mastered that one through these two exercises. Very intense exercise. Okay, or very intense exercises. The next approach is what we call the Taylor series expansion method. The Taylor series expansion. How do we deal with the Taylor series expansion in this case? So we need to then say, solve the differential equation given below by means of the Taylor series expansion to get the value of y at x equal to 1.1. Okay, now use terms up to x to the power 6. Delta x is 0.1. So you have 0.1, but we must go up to 1.1. Now, this is the differential equation in the case of the Taylor series expansion. Ordinarily, in the exam, you meet the Taylor series expansion, or you meet the Euler, or you meet both. Right, so to get the value of this. So now, if this is a differential equation given, these are the two initial values. Y at 1, for instance, equals 1, and y prime at 1 equals 2. And we want to solve this particular problem step by step. And we get started as follows. Now, there are certain things, obviously, we need to consider here as we looked at this one, but we remember that one thing with the Euler, we actually, with the Taylor, we actually have a repeated differentiation. So we then say, what have we been given? What do we recognize? Right, we have been given d squared y dx squared, which is xy squared, 2y primed, x primed plus this. Right, so minus 2y primed plus x primed plus 4. And then you would have that y at 1 is 1, y primed at 1 becomes 2. Okay. So we have been given that differential equation, but it is which is the second order differential equation. But also we have been given what? We've been given the two initial values, y1 equals 1 and y primed at 1 equals 2. Right, so what we then do is we approximate. Right, we approximate y at 1.1 by the truncated Taylor series. So we approximate y at 1.1 by the truncated Taylor series. And now we actually deal with the truncated Taylor series. What then is the truncated Taylor series? But how do we deal with the Taylor series? There are two things we need to take into account with the truncated Taylor series, but we do these obviously up to x to the 6th power. Now, what is all this? It means that whenever we have a y of x, it is in general y at 0. Y at a, okay, y at a, then when we have y at a like this, then you have the primed, like this. So we can write like before, I want to write the general formula here, and then we're going to go to the applications. Because this one is there 99.9% of the times. But you need to make sure you can be able to do the Taylor. So now, if you do the Taylor approximation or the simple Euler, right? And then we shall look at the other modified Euler, right? So this one, for instance, is the normally we write the plus, right? And if we write the plus, then we can write the x plus a, right? And normally we subtract. Yeah, you can subtract the a like that, and then you put the primed, y primed at a. Okay, you can divide by 1 factorial, and then now you're gonna have x minus a. What I mean, x minus a, and then if it is x minus a, which is what I'm saying here, then you're going to put y double primed at a, then you put 2 factorial, like that. Okay, so you have these. And then we have the square. Okay. And then you have these cubed 3. And then divide by 3 factorial. Let's write more terms. X minus a, you put 4 a 4 factorial. And then you have x minus a 5, y 5. X minus a 6, y 6. Okay. Now, so now you have this one. Now let us do this. So now you would have, okay, let us just approximate the thing now. So we're going to studying. So let us start with the approximation. So if we agree that the approximation, which is going to be y at 1.1. Y at 1.1, you can write it like that, but you can also say it's approximately because we have it's truncated. Truncated, we have removed some of the terms. And then now it's going to be y about 1 because this is at 1. And then plus, then you have 1.1 minus 1, which is going to give us 0.1. Y primed at 1. And then you subtract here, which is 0.1, you square it. Y double primed at 1 divided by 2 factorial. Okay, let us continue with this one. And then you would have 0.1, you cube it, 1. Okay, then 3 factorial. 0.1 to 4, which is 1. Yeah, then you have 4. Okay, let us see what we're getting. And then this is going to be exactly 4 factorial. And then we're going to go on. Okay, so what we do, because the pattern is very clear, you can remove some of the things here and then write the pattern, because now the pattern is clear that this thing is continuous and it goes on for more terms. So you're going to do like this, and then you're going to do 0.1, and then you raise it to 6 power. Y to the 6th power at 1. And then you divide by 6 factorial. Okay, so that is what you're getting. So this, therefore, becomes the formula we're going to use. And that is the general Taylor. And then we have the specific application of the Taylor, but also up to the terms of x to the power 6, up to the terms of x to the power 6 there. Okay, right. So with this mentioned, then we are most certainly in business. But there are certain things we need to do with the derivatives. The derivatives. The derivatives at x equals 1 are calculated. Are calculated in the way illustrated. In the way illustrated. Okay, on page 453 of Gerald's. Okay, Gerald is the book, the prescribed book. Okay, right. So now we then say that if they say whenever we have that the second derivative, y double primed becomes this, which is xy squared 2y y primed plus x cubed plus 4. Then let's evaluate this one at, because it's y primed at x. So if you evaluate it at 1, it's going to be 1 squared minus 2 times 1 times 2 plus 1 cubed plus 4, and the answer becomes 2, the third derivative of x. So if you find the derivative with respect to x, right, so the derivative of the x is 1, giving us y squared, and the derivative of the, and then now if you find derivative of the y, it becomes, so of the y squared, it becomes 2xy y primed by implicit differentiation. And this is minus 2y primed squared minus 2y y double primed plus 3x squared plus 4. Okay, and then now you can get this one. Y triple primed at 1, which is 1 plus 4 minus 8 minus 4 plus 3, and the answer is the negative 4. Okay, now that gives us the Taylor series expansion. Okay, we're doing some derivatives, but remember we must do up to 6 of the derivatives. So there are lots of them that we need to do, but we have done up to 3 so far, and then we need to continue, and then we're done. So this is easy for us. And then now let us go on. So if we say we've got the third derivative, and then we need the fourth derivative of x. The fourth derivative of x is 2y y primed. Okay, we're going to discuss this one. 2y y primed, just product rule and the sum rule, just differentiation. And then you can discuss if obviously there's a little problem. I'm trying to make sure that we move, because this is a bit easier. And then you have this minus 4y primed, and then the things you have not understood, you'll have to indicate. So minus the things you're not sure about, the things you have not understood. So minus 2y y triple primed plus 6x. Okay, this one is obtained. We differentiate again from the third derivative, and you get this one. Okay, and then with this mentioned, the fourth derivative of x is 2y 2y primed plus xy minus y primed y y double primed 3x. So 4 at 1, which is 2. And then 4 plus 1. And then you have 4 plus 2 plus 4. Okay. Because the y primed is, yeah, it's minus 4. So it's going to be plus 4. So y primed is minus 4. That's what we got. So this one is going to be plus 2 plus 4. Substitute the previous values we've got. Like substituting the y primed. Y primed is 2 from the previous calculation. X becomes 2. Then we have minus 6 plus 3. The result is 10. Okay, so we're not done yet. And then we continue with the differentiation. Now, from this third derivative, then we must get from the fourth derivative, we must differentiate again. I know it's a long thing, so I'm just going to write the long thing because you like differentiate term by term, right? In case you find that you're wondering, you have a question, you can always obviously get back. So the fifth derivative, it's long, but it's term by term, so it's going to be y primed, then 2yx double primed, 1, 2, 3, and then the plus y, term by term differentiation, the second derivative, and then the second derivative, and then x, y, the third derivative, and then the fourth derivative, and then close bracket, and then you have the second derivative, and then xy prime minus 3y double prime, and then you have y primed together with y primed plus x, y double primed 3y, triple primed plus 3, and then you close like this. And then after I've written all these here, okay, we understand that these can be simplified to this, which is 2y, 3y double primed, x, y triple primed, y to the fourth power, and then plus 3xy double primed minus 4yy minus 3yy squared plus 3. Meaning, now we substitute to find y5 of 1. Okay, to find the fifth derivative, we differentiate the fourth derivative. Right, and then if you substitute here in the place of the y, it becomes 1, 6 minus 4 minus 10 plus 2, 6 plus 6. Just substitute everything we've got from the previous steps. And then minus 3 by 4 plus 3. And if you add everything with the calculator, we get exactly 78, yeah? We're not done because we must go to x to the power 6. So we must differentiate this one more time. Okay, we differentiate from this step. Differentiate from this step. Find the derivative of each of the terms. And if you do, it's a long thing, but it is the following. Okay, let's try. Okay, we've got the fifth derivative, but if we differentiate it once more, we're going to get 2, then we have y, we differentiate term by term, and then it becomes 3y that plus xy that. We use the product rule, please. And term by term differentiation, wherever there's a product, we use the product rule of differentiation like we do in first year calculus. And then it is a 3y triple primed plus y. I'm just writing the terms here because I know that it can take a lot of time to just claim that we want to discuss term by term, and then it is the fifth derivative, and then you close like this. Then it is plus, but then we have minus 6y double primed and triple primed like this. And then Um, okay. Then you're gonna have this one together with plus y double primed, 3y primed, 3x, y double primed minus 4y triple primed plus y primed. I know this is long, but it's term by term differentiation from the fifth step. 3y double primed, 3x, 3 derivatives, 4y to the fourth, and then you close like this. Okay, if you do everything, you add all the terms up. You must be able to get 2y, 4y triple primed axy to the fourth power minus y to the fifth power, and then 12y double primed 4xy triple primed to the fourth, and then it is 3xy minus 10y triple primed. So that in the end, then you have 6, 1, which is 1 minus 16 plus 10 minus 78. Substitute everything we've got before. 2, substitute 24, substitute 16, substitute the minus 50, substitute the 2 and the 40. Right, getting everything here becomes minus 152. I don't want us to waste a lot of time there. Okay, right. So now, if we substitute all these values, we get, right, if we substitute, I know that the derivatives are like too many. All right, if we substitute these values, right, in 1, which is the first thing we've got, we get, so you'd remember that the one we're talking about is this one here, y at 1.1, which is approximately y at 1 plus 0.1, y primed at 1 plus 0.1 squared. Okay. But this 0.1, let me write it clearly here. Okay, we got this one before, but remember it's going to be y 1, and then, okay, we're going on, please. And then it is plus 0.1, and then y primed at 1. We got this one from the Taylor formula, original. The formula I wrote in the beginning. So is this one divided by 2, y, like this. You can put 2 factorial. So we have plus, okay, yeah, this y double primed at 1, and then you have 0.1, you cube it, 3 factorial, 0.1 to the fourth. So now, at 1. At 1, this one, but also this one, you do it at 1. Okay, you calculate it at 1. Okay, you do it at 1. Okay, okay, this is the formula for the Taylor, please. But now we applying it to this problem. So it's 4, then do 5. 0.15 over 5 factorial. Then you're going to do the fifth derivative, but you calculated it 1. Then you're going to do 0.16. Then you have the sixth derivative at 1, and then divided by 6 factorial. So that in the end, you have y 1.1 approximately. What is y at 1? Okay. Some of the things you know that y at 1 is already 1, and then you got 0.1. Y primed at 1, we got it before. Right, so we got y primed at 1. And then I'm just going to show some of them. Right, good. So I'm just going to show some of them, and then we shall go on. We're just going to show some of them, and then we shall go on. So because we have already got the rest of those, so what we then do is we plug everything in. So the rest of the terms would be what? So it would be that. Right, if you substitute all these values at these, you get 1.1 is approximately minus 1.20, 1.209381. Right, 81, then 289. Okay, yeah, okay, welcome the Anika. So you're gonna have exactly this. So now if you look at this, okay, how have we got this? We got the y at 1, y primed at 1 is substitute. Y double primed at 1 is substitute. The y triple primed at 1 is substitute. Y quadruple primed at 1 is substitute. The fifth derivative is substitute. The sixth derivative is substitute. Using a calculator for everything, then you'll get to this. I know it's a bit lengthy, but you'd remember that at this point, what we have becomes the following. I need to show that obviously we got the rest of the steps we need, like, okay, this is y at 1, which is according to Taylor, it's this, but the general Taylor expansion is this. Now, you then come here and then say, what is y primed at 1? Y primed at 1 is 2. And then what is, for instance, y triple primed? It is this, and therefore y triple primed becomes exactly that. Okay, and then you have the fourth derivative. Okay, right. And now getting all these. Right, getting all these. So in a nutshell, what we're saying here is this is y double primed. Okay, this becomes y double primed, yeah? So this becomes y double primed, and then if it becomes y double primed, which is equal to 2. So y triple primed is minus 4, because y primed at 1 is 2. So, but yet the double primed is also 2, as much as the single primed is also 2. So you take all those, you substitute here. The y primed is y primed at 1, it's 2. The double prime is also 2. The triple prime you've seen there, and so on and so forth, and you get this. And this becomes obviously the required results. However, we actually say the following. Yeah, let's just say the following, then we're done. Okay, now to conclude, we then say actually the exact, because we got some estimate, approximate. So we conclude and then say actually the exact value rounded to 10 significant figures. Right, 10 significant. Right, 10 significant figures. Right, so rounded off to 10 significant figures. Right, say significant figures. Rounded off to 10 significant figures. Can be calculated. Right, can be calculated by adding more. By adding more of the of the Taylor series to 1. Right, which is the first thing we've got until it is clear. Until it is clear that you're finishing, please. Further addition. Until it is clear that further addition of terms will not alter the 10th digit. Will not alter the 10th digit. Okay. Right. There's another. Right. So, um, okay, yeah, these are four, it's enough. And so obviously we've got the answer. What is the answer to the problem? The answer to the problem is this one, because so use the terms up to x to the power 6 to actually solve the differential equation below by means of the Taylor series expansion to get the value of y at 1.1. That is the answer. Right, we must thank you for joining us. It was awesome having this discussion. Right, we shall continue the next time. We'll talk, I'm sure, on WhatsApp. Okay, yeah. Thanks so
Thank you.
much. Thanks so much for the discussion. Yeah, we were trying to squeeze in this Taylor, but it's a bit long. But yeah, I'm sure that you've got a sense of what we need to do. But obviously, we'll discuss on WhatsApp and see what you need to do next, what the plan is next. Right. So we're gonna send you the recording, obviously, in the afternoon. But thank you so much and enjoy your
Thank you.
day.
Thank you.
Okay, thanks, dear. Goodbye.